Here's question 3. It says a model aircraft was tested in water at speeds from 15 to 17 meters per second with drag forces as shown from about 200 and some up towards 300 newtons. And the projected frontal area of the model was 0.035 square meters. If the prototype was going to be the same shape but 3 times as long, so 3 times as big in all dimensions, and operates at low altitude in air, what's the velocity range for similar flow behavior in the prototype? So velocity range for similar flow behavior, if we're going to have similar flow behavior, we've got to have the same Reynolds numbers. Reynolds number for the model must be equal to Reynolds number for the prototype. So velocity for the model times the length for the model divided by the kinematic viscosity for the model must be equal to velocity for the prototype times the length for the prototype divided by the kinematic viscosity for the prototype. So if we want to know the velocity relationship, then we know the model velocities. We'd like to know the prototype velocity. It will be equal to Lm over Lp, so bigger prototype goes slower, times nu p over nu m. So a different viscosity will change the speed as well. So if the prototype viscosity is higher, then the velocity will have to be higher, all times the model velocity. And that's going to be length of the model over length of the prototype, 1 over 3. And viscosity for the prototype is going to be operating in low altitude air. So the kinematic viscosity will be about 1.5 times 10 to the minus 5 meters squared per second, divided by the kinematic viscosity for the model. If it was water at 20 Celsius, that will be about 1 times 10 to the minus 6. So the air is about 15 times higher kinematic viscosity times the velocity for the model. 15, factor 15 on the viscosity, factor 3 here, together that gives a factor of 5. So 5 times the velocity for the model, going from 5 times 15 is 75, up to 17 is 85. So 75 to 85 meters per second. That's part A. Part B says, estimate the drag force on the prototype at a speed of 83 meters per second. Conveniently enough, that falls into our modeled range. So we're going to be interested in looking at the same Reynolds number. So our corresponding velocity will be 83, will correspond to 16.6. And if we go up here and we assume it's linear, that gets me a drag force of about 275 for the corresponding conditions for the model. So I expect to see, if I'm at the same Reynolds number, the drag coefficients to be the same. Drag coefficient for the model equal to drag coefficient for the prototype. For the model, that'll be the force of drag on the model divided by 1/2 rho for the model, u squared for the model, and area for the model, equal to force of drag for the prototype over 1/2 rho for the prototype, u for the prototype squared, and area for the prototype. So if I want to get a prediction for the drag force on the prototype, the halves will cancel out, and I'll wind up with rho prototype over rho model. so the density ratio has an effect on how big the force will be. I'll wind up with the prototype velocity squared divided by the model velocity squared, and I'll wind up with the area of the prototype divided by the area of the model. So increases in density, increases in velocity, increases in size, all increase the drag force, and then I'll multiply by the force of drag on the model. That'll be, for the prototype, about 1.2 kilograms per cubic meter divided by 998. For the model, the water, the prototype velocity is going to be 83 squared divided by the corresponding velocity 16.6 squared for the model. The area of the prototype over the area of the model, well, it's a 3-to-1 ratio for the length scales, but for the areas that'll be length squared, so it's not 3-to-1, it's 3 squared to 1 times, we read from up here, 275. So, plugging those numbers in, 1.2 divided by 998 times 83 squared, divide 16.6 squared times 9 times 275, and I get 74.4 newtons. 74.4 newtons is the force that we expect on the prototype.